To solve this, our project introduced an integrated onboard hybrid energy storage system or HESS that combines an NMC battery pack with an ultra capacitor bank. This system is managed by an interleaved bidirectional buck boost converter governed by model predictive control. The ultra capacitor bank acts as a buffer, absorbing high-frequency current transient and shielding the lithium-ion cells from those damaging spikes. Furthermore, we complement the vehicle with a stationary, smart BESS-backed charging kiosk to provide active grid peak shaving and intelligent load management. Hello everyone, as urban centers shift away from internal combustion engines, the electrification of lightweight two-wheelers is accelerating rapidly. However, conventional lithium-ion battery packs in electric motorcycles suffer heavily from limited power density. High current spikes during rapid acceleration and generative braking cause several thermal stress, leading to premature battery degradation and a reduced vehicle life cycle.
Let's move on to problem statement part. For the first problem, we have limited charging access for electric motorcycle. Electric motorcycle is cleaner and cheaper to operate, but however, charging facilities are still limited. So this make user less confidence to depend on electric motorcycle for daily use. Next, grid charging is not always flexible. Most of the EV charging system depend directly on the power grid because it provides continuous electricity, existing infrastructure, and also sufficient power for daily charging. But this is not suitable for all locations, such as parking area, campus, rural areas, and also temporary charging station. And a fixed grid connection can increase installation costs and also reduce charging flexibility in remote or temporary locations. Therefore, a more flexible charging source is needed. Next, voltage mismatch problem. The battery energy storage output voltage may be different from the voltage required by the electric motorcycle battery. For the example, if the BESS is 96 volts in DC and the motorcycle battery is 72 volts in DC. So to connect it directly, it will be unsafe. And without proper voltage regulation, charging may cause overvoltage, overcurrent, overheating, and also battery damage. Therefore, the charging voltage must be regulated before charging. And for the last one, unsafe charging without proper control. So, without proper charging control, the output voltage and current may become unstable during electric motorcycle charging. So, we have to take note that uncontrolled charging may cause overvoltage, overcurrent, overheating, battery degradation, and also short circuit risk. So, this shows that electric motorcycle charging requires proper voltage, current, and safety control. So, the problem is not only charging access, but also charging safety and battery connection.
Hi, my name is Fahim from Group 2. I will present the literature review for our project on BESS power buck converter charging system for electric motorcycle. First, electric motorcycle charging in Malaysia still has several problems. Charging stations are very limited and mostly available in big cities. Many riders, especially delivery workers and students, face difficulties finding places to charge. This causes range anxiety and slows down the adoption of electric motorcycle. One good solution is using BESS or battery energy storage system. BESS can store electricity during off-peak hours and release it when there is high demand. It is called peak shaving. It helps reduce pressure on the grid and makes charging more reliable, especially in areas where the grid connection is weak. To charge the motorcycle from the BESS, we use a buck converter. The buck converter steps down the voltage from the BESS to the level needed by the motorcycle battery. It is simple, efficient and low cost, which makes it sustainable for electric motorcycle and usually need between 1 to 5 kW of power. However, most existing studies focus on high power charge for electric car. There is very limited research on simple buck converter system powered by BESS, especially for electric motorcycle in Malaysia. So our project tries to fill this gap. In short, electric motorcycle adoption in Malaysia is limited to the poor charging infrastructure. BESS can help through peak shaving, and the buck converter is suitable because it is simple and efficient. Our project offers a practical and low-cost solution using basic power electronics knowledge. Thank you. That's all for the literature review.
Next, let me explain the methodology of our proposed charging system. The aim of this project is to develop an battery energy storage system using a BESS. Instead of rely fully on the power grid, the BESS stores electrical energy and supplies it when charging is needed, reduce grid dependence and improve charging stability. Our system consists of 4 main components. First is the BESS, which uses a battery that can store electrical energy. This battery was selected because it is efficient, safe and has good thermal stability and long lifespan. Second is a DC-DC buck converter, which regulate the voltage and current from the BESS to match the charging requirement of the electric motorcycle battery to ensure safe and efficient charging. Third is a battery management system, which is a BMS, which monitor battery voltage, current, temperature and state of the charge. It also protect the system from the faults such as overvoltage, overcurrent and overheating. Finally, the regulated power is delivered to the electric motorcycle battery for charging. To evaluate our system, we focus on 3 performance indicators, which is charging efficiency, energy utilization, and charging reliability. Overall, this methodology aims to develop a charging system that is safe, efficient, reliable, and reduce dependence on the electrical grid. Now, I will continue with the result and discussion of our project. Our proposed charging system successfully integrates 4 main components. First is the battery energy storage system, BESS. Second, DC-DC buck converter. Third, BMS, battery management system. And lastly, the electric motorcycle battery. The BESS stores electrical energy and supplies power for charging. The DC-DC buck converter regulate the voltage and current using PWM control for efficient charging. The BMS monitor the battery voltage, current, temperature and state of the charge while providing protection against overvoltage, overcurrent and overheating and undervoltage. It also performs cell balancing to improve battery life and safety. Finally, the regulated power charge the 60 volt 40 ampere lithium-ion battery, which then provide energy to the motorcycle for normal operation. Overall, the system ensures safe, efficient and reliable charging for electric motorcycle. From our cost analysis, the total estimated cost is about 6,000 ringgit. With the battery energy storage system being the most expensive component because it is the main energy storage unit. Other components such as the buck converter and battery management system are essential for efficient and safe operation. Although the initial cost is high, the system offers stable charging, higher efficiency, lower energy losses, reduced maintenance cost, longer battery life and support renewable energy for a more sustainable solution. It can also encourage greater public confidence in the electric vehicle. And lastly, this can show the 12-week project schedule, starting with the literature review, followed by system design, simulation testing, and finally, report preparation and presentation. It's helped keep the project organized and on schedule. In conclusion, this project demonstrates how a battery energy storage system can improve the safety, efficiency, reliability, and sustainability of the electric motorcycle charging. That's all from me. Thank you.
Through comprehensive hardware simulations, our key achievements have been successfully validated. First, we achieved a 15% extension in battery life cycle thanks to ultra-capacitor current buffering. Second, we demonstrated a 12% improvement in urban driving range under real-world duty cycles. Finally, our setup successfully preserved overall system efficiency within strict motorcycle chassis constraint while enhancing grid stability via vehicle-to-grid peak shaving. Ultimately, this project validates a scalable, technically sound model that beautifully balances electric vehicle performance with utility grid integrity, driving us closer to a sustainable urban electromobility future.